Hello everyone. Today we'll be working on an HDLBIT problem, and it's called carry select adder. So in this problem, first I'll explain the previous problem. So we had this adder called right here, ripple effect adder. And basically what this adder does is, you see how it says add 16? Basically, if you have a 16-bit number, what it's going to do is it's going to have 16 add 1 modules, and then add each of those numbers, each of those bits, right? But in case you didn't notice, what we have in here is a problem where it's not as efficient. So in order for this to run, what has to happen is everything in here has to run finally until it gets the carry out, and the carry out is inputted into the carry in, right? But what if there's a more efficient way to do this, where the carry in is already defined, right? We know the carry in can only be two options, right? It can be a 0 or a 1. So there's this really efficient way, and it's called the carry select adder. So as I mentioned, that's the ripple carry adder, and this is the carry select adder. So some of it's the same, right? This top module right here, it's pretty much the same, where we have a carry in with the 0 and add 16, right? Half of the bits, half of the sum is already defined, but now we have to do the other half. So we have two add 16 blocks here. And what happens is this is running parallel. So while this is running, we have found our carry out. Now we know our carry out is either going to be a 0 or a 1. And since both of these ran, we also know the sum. We already know this answer. And so using a multiplexer, we basically can select, carry out was a 0, so this is gonna, the output, this wire, is gonna be the sum of this. Or if carry out was 1, this is gonna be the output. So in case you don't know, that's how a multiplexer works, right? A multiplexer has two inputs here, and then one select input, which basically just selects which of the inputs to use. And this is portrayed here where the C out selects which input to use, right? It either outputs this one or this one, right? So I'm gonna just recap one more time. So we have two inputs here, A and B. Half of A and B go into this adder. The other half go into both of these, right? So half of A, half of A, half of B, half of B. The only difference in here between these two is this carry in, right? In the previous example, this carry out was connected to here, but we don't have to do that because carry out can only be 0 or 1. And so when this is already defined and we already have the sum, all we have to do is, carry out is 0, so this is going to be the output. Oh no, carry out is 1, and then this is going to be the output. So that's kind of how it works. But how do we code this? Let's get started. So we have our module declaration. So our input, 32 bits, right? A and B, and our output is 32 bits with the sum. So in order to add this, let's get started. The first thing I like to do with a problem like this is just sort out the wires. So we are going to need a couple wires. We're going to need one wire for here, one wire for here, and one wire for here. This is basically just, we know the output, but since we want to choose and plug them into the multiplexer, we want to specify the wires. Also, since these are two of the same adders, we should specify which, we should separate the wires. So that's another thing. And then we need the wire for the carry out. So we can define 3 wires. And this is a 16-bit wire called W0 or wire 0 and wire 1. right? We have wire 0 right here and wire 1. So basically wire 0, carry in 0, wire 1, carry in 1. Next, we're going to make a wire W carry out. So here's our wire for our carry out. And this is going to be the select portion of the multiplexer. Also, in case you were wondering, this is called a 2-to-1 multiplexer, where there's 2 inputs and 1 select. Okay, now we can start instantiating our modules. So we create one module, right? Our module is named add16, all 3 of these. Add16, and then we're just going to give them appropriate names. So we can say instance main, and we can just plug in these inputs here. Now I'm going to go by, there's 2 ways of inputting these. You can just go .a and then put your input in, but I'm going to just go based on position, right? So just as long as your inputs follow this guideline, right, then everything should work. So following our guideline, we have A goes first. Well, we want to put in 15 bits of A. And then B goes next. Same thing there, 15 bits of B. And this is just going to be your typical adder. Make sure everything's good there. A, B, 0. So 0 is our carry in. So this is also specified here. Carry in is 0. And then our sum, 15 bits, the first 15 bits, and then our wires are carry out. Perfect. Okay. Now we'll create, and we have to create 3 of these modules, right? 1, 2, 3. I'll call this inst add 0, right? Because our carry in is 0. And so remember, this does do 15 bits, but it does the last 15 bits, right? So instead of 15 to 0, it takes up 31 to 16. 31 to 16. And then also, one thing I did forget. One thing, you know what? I'm just going to make this 0 for now. That's good. All right. So this is our add 0. So now what we're going to do is we're going to make an add 1. Pretty much the same process. Just wire 1. Also, this is 1 because that's the most important part. It's the carry in, and then that looks good. All right. Now this is the part where an HDLBIT got kind of weird, right? Because if you are following along, it randomly introduced multiplexers, which are a little bit hard to code. And in this stage, since it didn't talk about if statements, we can use the always. So always, think of it like this. Always, it's like it's always certain, or it's always gonna happen. That's sort of how you think about combinational logic, right? Combinational logic is just like, imagine you have a box, right? Our combinational logic box, and just no matter what you put, it's gonna output, you know, some sort of operation, right? Nothing ever changes. You put something in, it's gonna keep doing the same thing. That's sort of what a combinational logic is. It's just like almost like a calculator, or like a calculator that does one specific thing. Okay. So, and then we'd use the @ symbol. This is just, you know, syntax. And then in the brackets, we put an asterisk. So if you've done other programming languages like Python, for example, and you've ever imported a library, you'll know that asterisk usually means everything. And that's the same in this scenario, where we use everything. So let's just begin, you know, it's the same as saying, you know, module and end module. At the end, we'll also have end case, or we'll have end. So now we're going to create a case. So case just means, you know, in a multiplexer, what is the selection? Or no, it's really the case. We're creating like almost like a truth table, if you've ever, you know, experienced with those. They're just a table with, you put 1 or 0 in, and it gives you an output. So here we're using W carry out. Why? Well, because that's our selection right here. These are the inputs and these are selection. Selection is usually on this slanted portion of the trapezoid, and the inputs are on the flat side. That's a good way to tell. We have our case. Now inside our case, we want to say the specifics. What happens if this is 1, this is 0, right? Basically in our case we say if carryout is 1 or 0, what happens? And here we pointed that, okay, this should be outputted when this is 0, when the carryout is 0, and this should be outputted when carryout is 1. So the 0 and 1 means, if carryout is 0, this outputs, and carryout is 1, this outputs. So we have to define this. So we say 1, B, 0. And if you haven't had this or experienced this, it basically just says 1 bit in binary, and then the number in binary. So now we're saying, okay, this is what WC out was, or W carry out was. Now what happens? What is our expectation? Well, our expectation in this case is that sum of 31 to 16, right? As we define here, 31 to 16 should be this output. So sum 31 to 16 equals, right, wire 0. And wire 0, remember, we defined here, and that's this wire. So this means that this wire is equal to the sum of 31 to 16. We can also say W0, we can reverse it, doesn't matter. So 1 bit, right, binary, the number's 1. Pretty simple. Sum 31 to 16, like before, but like you probably have guessed, equals to W1. Okay, that's pretty much the end of the description. Now we just go end case, and then we do end, because begin, end, case, end case. Very similar to like C brackets or just any brackets in any software coding language. And yeah, that's about it. Let's run this and make sure it works. I think everything looks fine there, and it works. Great, success. So I'll just run through it again. So we have wire 15, 0, wire 1, 16 bits, wire 0, and wire 1. And then we have a 1 bit wire carryout. You might be asking, well, why didn't you put a 15 0 here? That's because wire carryout is only a 1 bit, right? Because it's either a 0 or 1. And we also defined that. Let's prove that here. And so this is just creating 3 modules. And the one thing that is actually it's usually used is instead of having 0 as your carryout, you can sometimes just use an extra wire, right? Because in here, you're not outputting a carryout, right? So for correct syntax, you can just say wire extra, sort of like a dummy wire, and you just put extra here. Don't worry, it works. It's just doesn't have any function for it. So we run it, and there it is. I hope you enjoyed this video. I hope you learned something from it, and yeah, keep practicing, keep coding. Have a good one.